This is the outline of my talk, but first of all, I would like to tell you where Newcastle, Australia is. So if you can imagine Australian continent, and this blue sector is New South Wales. And it has two major cities, the national capital, Canberra, and Sydney, the biggest city in Australia. So 150 kilometers north of Sydney is Newcastle. You can get there by car. It doesn't take long, but it takes much longer by train. So that tells you how fast our trains are. So how does it look like? Something like this. This is our signature landmark, the Nobby's Head and the lighthouse. And city goes from there over that side. Up. And what do we do in Newcastle? Similar to Chile, we dig coal, we dig minerals and sell to China. And we also very much like our climate and nature. And I personally like this aspect ratio. It makes me look very slim. We also grow grapes and turn into wine. And you can see there are a few similarities with Chile. Not to mention that those guys are Chileans as well. They're my friends. Okay, and what's special about University of Newcastle? The first special thing is you cannot find it in the bush. If you look at it from air, you can see nothing. It's very nicely hidden behind the trees, and although we have about 25,000, more than 25,000 full-time students, the first semester of each year starts with thousands of stray students wandering around trying to find a building, because they spread very, very wide and they're very well hidden. Same thing happens to the visitors. So if you go to Newcastle, Australia, you have to have a map of the campus. But engineering is quite easy to find. It's just across the road from Chancellery, if you manage to find Chancellery. So the other special thing about Newcastle University, and you may be familiar with this book, that's where it comes from. Professor Graham Goodwin, who I'm fortunate to work with, in collaboration with Mary Salgado, who's from University of Santa Maria, wrote this book, and Stefan Grabe. Okay, so I move to the topic of my presentation. It's about model predictive control in power electronics and how to make it work better. So after this morning's presentation of Professor Holtz, I would like to change that to 1980s now, because it's 1987 that predictive control was introduced to power electronics, as I know now. And it's very popular, and what is sort of special about MPC is that it is traditionally seen as something completely opposite or alternative to classical control. While in this work, I'm going to show that, in fact, there are a lot of similarities, and in fact, the classical controllers are actually MPC in a certain sense. And I will also present you an MPC-based framework to address the challenges of power electronic system. And as you can see, I have a lot of writing in my slides. There are a few slides, but I put most of what I'm saying on slides so that people can read. Okay. So if I use current control as an example, then model predictive control is typically implemented the following way. You measure currents, then you predict, based on the model, you predict the load currents for the next sampling interval. Then for all possible switching states, then evaluate the cost function for each of the prediction, and then select the switching state which minimizes this cost function. Well, this is typical cost function, quadratic cost function for the tracking error. And then apply the new switching state. However, it's completely same thing if you do it in slightly different order. You measure current, and then using the load model, you determine which voltage you would like to have to bring your current from measured to the predicted, to the reference in the next control cycle. So if model is this, then your desired voltage, the optimal voltage, will be this, simply the inverse of the plant model. And then from the available set of the voltages, you choose the one that is as close as possible to the one that you want. So you're essentially minimizing this cost function. Now, it is easy to show that voltage that minimizes the first cost function also minimizes the second, so it's the same thing. But if you put it in this form, then it becomes very obvious that finite set MPC that I just described verbally is actually a sort of proportional controller. You have a feedback, you have some gain, and you have just a gain in its forward branch. So model predictive control probably can be utilized better to achieve better performance. Okay. So I'm going to present the broader Mpc formulation, more general Mpc formulation, based on two fundamental concepts, linear steady-state Kalman filter and internal model principle, which basically tells you if you want to get rid of disturbance, put it in your model. And it's kind of different from the typical or standard MPC in the way that typical MPC usually explicitly uses the model-based prediction and cost function minimization in its algorithm. But here, the same thing are used, but they're implicit in the controller design. So I start with state space form of typical power electronics application, which looks something like this. And please note there is a disturbance also, which is also part of the output. For example, if you have a linear RL load, then this is your parameters of the load. If you have a constant disturbance, then the corresponding matrix is just 1. If you have a sinusoidal disturbance, then the corresponding disturbance part is this. And multiple or periodic disturbances have something like that in their disturbance model. Now, for this system, it is very well known how to formulate Kalman filter. And this is how it looks like. So there is a estimation for both state variables and for the disturbance. And the output in innovation form will look something like this. Okay. Now, it is probably less known, but proven in control theory that exactly same system, exactly same innovation form can be described in polynomial form, where all these polynomials can be derived from the model parameters and from the Kalman filter gains. So Kalman filter gains are present in this. Now, polynomials are usually start with 1, but if they do not, you can always scale them, except for the B, which is the, comes from the plant model, and it usually has a 1-step delay. So for example, RL load will have this is I polynomial, and this is B polynomial. And for constant disturbance, D is something like this. Okay. I'll have some polynomials in the next few slides, but once we're over it, there is no more formula, very little formula afterwards. So this is the framework that I'm going to present. We start from this polynomial form, that is the alternative way of this Kalman filter, and then we divide both sides by polynomial C. Then the left-hand side can be factored into 1 and the rest of it, and the purpose of this factoring is to separate the most recent output from the past values of output. So everything on the right-hand side is now in the past, and the recent value is on the left-hand side. From there, we can make a 1-step ahead prediction. So now this is our predicted value in the next step, and all these things have the order of Z0, so they're either in the present or in the past. Now I factored this part again into the most recent one and the previous or the past control values, which already happened. I know them, but I cannot change them. And then at this stage, I apply the quadratic cost function of the difference between the reference and the predicted output. clearly this cost function will be minimized if this is made equal to that. Then the cost function will be simply 0. And now the only control signal, or the only control that I can use to minimize this cost function is that latest, the control UK, which is not determined yet. So everything else already happened. And now I express, so from here, I express this control UK. And that is the one that will bring me in one step the predicted output to the reference. This is my optimal and unconstrained control law, which minimizes the cost function. But if there are constraints, then if it's outside the constraint boundary, I have to make it as close as possible to the desired. Okay. Worked example. So let me take an RL load with a constant disturbance and do the steps very quickly. So this is my A, this is my D, this is my B, D again, and this is C polynomial that I don't know yet. I divide by C, I factor the left-hand side, I do one step ahead prediction, I factor the control, I apply quadratic cost function, I minimize it, bring it to 0, and this is my optimal control value. So this is the voltage that I have to apply now to bring the cost function to 0. And if I cannot apply that, I apply the closest one that I can from the available set or available constraint region. In a special case where C is made equal to A1, then I will have something like this. And this is easily recognizable as proportional integral controller. So in fact, PI controller is MPC. But MPC for a particular model of the plant, it is first order a linear plant, and for a particular disturbance model, which is the constant disturbance. And this is something that we all knew, of course. So anti-wind-up form of the PI controller I just received is this. And if you modify it into more conventional form, it will look like this. So obviously, it is a PI controller. Now, doing exactly the same things. OK, result. Sorry, I jumped there. For linear first-order RL plant with constant disturbance, we designed MPC controller, and the result is PI controller with a recommendation for the gain and for the time constant. Such a controller is implicitly MPC. If we do exactly the same thing but assume sinusoidal disturbance, then a proportional resonant controller will result. So this control is also MPC. Implicitly, it minimizes cost function, and it uses prediction based on the model. All right, it would be all very nice if all the power electronic systems were as simple as that. Unfortunately, they are not. So there exist practical challenges, and I will show how we can address them. There are transport delays, there are nonlinear distortions, there are nonlinear switching delays, and then there are also challenges on the implementation side, such as how to choose Kalman filter gains, how to minimize numeric errors, and also philosophically, we would like to include additional objectives. For example, switching losses or voltage balancing or noise shaping or some other objectives in the control design. Okay. I start with transport delay. Transport delay is something that we deal in every power electronics application, and it comes from the following. In cycle 1, you measure currents and calculate your voltage. In cycle 2, you apply this voltage, and the effect of this voltage will be only seen at the end of cycle 2. So there is one step delay, at least present, that allows this calculation before implementation. And what happens, it's actually significantly degrades the performance of the control because it reduces the bandwidth of classical controller. In a finite set MPC, it causes oscillations around the reference. So in classical control, it is dealt usually by designing controllers with maximum bandwidth you can. And in FS MPC, they usually advance the prediction by one step in future. So in our MPC framework, it's very easily solved, because basically what happened, we just have an extra delay in the plant. Let's include it in the plant model. And with this extra delay included, we do exactly the same steps, and automatically we have the optimal control structure for this case. That control structure will be something like this in anti-wind-up form, and I call it modified PI controller because it's for the constant disturbance. And this is modified PR controller for sinusoidal disturbance. And in the results, you can see if delay is not included, you cannot probably see it, but because it's very small, of course. But transport delay is present in the top picture and is completely disappearing in steady state in the bottom picture, because the control is so designed that it accounts for this delay. Okay, unfortunately, power electronics loads are not necessarily linear. And non-linearities happen, for example, due to saturation of inductances. So if you apply the sinusoidal current to an inductor which is saturating, then projecting through the magnetization curve, you get current that looks something like this. And it has all sorts of harmonics. The triplet harmonics usually disappear, and then you have 5th, 7th, 11th, 13th, these typical harmonics. I will not go in detail, just show the results. So how to address that? Include the disturbance in the model. So you have now disturbances at multiple frequencies. Particularly strong ones are the first 4, 6. Include them in the disturbance model and design it with inclusion of that disturbances, and that automatically eliminates them. So you can see there are harmonics in the voltage, but in the current there is none. Why it was possible to eliminate those harmonics? So why is it possible to control nonlinear plant using a linear model? This is because you can think about this MPC-based control as a combination of observer and controller. Observer simply looks at the errors at frequencies that you tell him to do. So these frequencies eliminate me the errors. So observer looks for the errors at these frequencies, and if it sees the errors, it tells controller, and controller kills them. So it doesn't really matter where these frequencies come from. If they come from saturation or they come from external harmonics, they will be eliminated successfully. So that makes the accuracy of the model is not very important. You can control a nonlinear plant with a simple linear plant model. Now, the practical challenges include Kalman filter gain design. And if you ever designed a Kalman filter, you probably know that it's very nice in theory, but in practice it's really painful, because there are a lot of parameters that are related to statistical properties of the noise, which you don't really know. So at the end, the Kalman filter becomes something with multiple tunable parameters that you tune in practice and then proceed to tuning the next one and so on. So that is not very easy to do. However, we found how to do it in this framework. Essentially, we reduced the Kalman filter gains to just one parameter that has a very clear physical sense. It basically just the distance between the pole and zero. By controlling this distance, you are controlling the width of the rejection band around that particular frequency. And that is also a special case of Kalman filter, which is optimal for the given model and disturbance. Okay. If you start including more frequencies in the disturbance model, then the transfer functions become very big. So it's multiple order transfer functions, which of course are hard to implement. There are two things to do with that. One is to convert the direct form into parallel form in the second order sections, which are easy to implement. And then instead of shift implementation, use delta implementation. So if you've done the digital filtering, this is the shift implementation, and you can see this is just a first order filter. You can see this multiplying coefficient is very close to 1 typically, and that's where numeric errors come into play. But if you do exactly the same filter in a delta implementation, this is what you get. So there is a very small coefficient there, and it's good for accuracy because it's small, so you can scale it to achieve the best accuracy. and dramatic effect to the performance. So with this approach, we were able to reject up to 8 different frequencies or implement filter of order 16 with a very, very basic processor that we're using in the lab. So I move to, okay, the additional objectives, of course, are important, and I say very briefly how to include that. So it is, this strategy is the best for the trajectory tracking, because you need to have this quadratic cost function as formulated in this way to be able to apply this approach. If you add, for example, voltage to the cost function, it's no longer going to work. However, if you notice, I've never mentioned modulator in the entire presentation, because this control is around modulator. Modulator is the device that actually imposes the constraints. And these constraints can be convex or non-convex. Convexity is not important. For example, finite set Mpc is very non-convex constraint. It's individual voltages. So what we can do, we can design a modulator in such a way that it will take care of these additional objectives. Minimize switching frequency, prefer or avoid particular frequencies, and so on. And we are working on the feedback principle around modulator to achieve those. Okay, so I'll show experimental results, and there are a couple of settings. This pair of experimental results show you the conventional proportional resonant controller versus our optimal. You cannot see the transport delay compensation. It's present there, but it's only 4 channels that I could use to show. But even the transient performance is much better in the controller that is specifically designed to account for transport delay. And another experimental setup that includes drive application with the motors on the test bed. We implemented those rejection of frequencies. And the first raw results were not particularly good. There were lots of low frequency noise. But that was due to 2 things: dead time and variation of the capacitor voltage. We compensated for those in the algorithm, and we got something that looks as good as that, and it's experimental results. So the rest of the noise is distributed evenly, because this is what we wanted to do. We wanted it to be almost like white noise with rejection at particular frequencies. And it was successfully achieved. So in summary, in this work, a broader interpretation of MPC is presented. Classical control schemes are special cases, and somehow they may not necessarily match the real loads, but we can improve them by matching the load model and disturbance model to the real power electronics application. We connected theory to practice and validated by simulation and experiments. So far, we implemented these ideas on inverters, 2-level and 3-level, and in the AC drive and grid-connected applications. But I'm open to suggestions for collaboration to use those things with new and interesting power electronics topologies. So this is my email address. And each time I come to Chile, I'm trying to learn at least 1 more word in Spanish. So I looked up in Google Translate, and this is what it gave me as questions, preguntas. But then Luis Moran was presenting yesterday, and he put consultas. So I put 2. I don't know which one is more appropriate. Hopefully, at least it makes sense to you. So thank you very much.